Whether or not a specific subject is boring or interesting, whether it is difficult or simple, whether you find it very interesting to go ahead with the subject or you find no, it is not my cup of tea, all depends upon whether you're getting the right guide, the right path, the right kind of book, and the right mentor who would take you through the wonderful journey of that specific subject. Topology is considered often to be a subject which is very difficult, which requires really, talented people who can only learn this specific subject, which has got a lot of abstract thinking, and hence topology is not within the grasp of normal or general people. In this particular video, what I'm going to do is that I'm going to give you a complete roadmap, resources, books, the way of study, where you should go, how you should learn, and specifically a different aspect of topology which will make this specific subject very interesting and a wonderful journey that you will take this specific subject in due course of time. This video is going to be a complete guideline in terms of YouTube lectures, books, online resources, guide, path, methodology of studying topology. And I'm sure by the end of this video, there is a pleasant surprise for you, which is going to make you happy and which is going to take you through this wonderful journey of this subject, which won't be considered something incomprehensible or something difficult. That is the objective of my video, and my name is Shaunak. I teach in a college and I welcome you to my channel where you're watching this video, Physics for Students. As this would be a complete journey for you to understand and learn topology, right on your screen let us see what are the topics we are covering. So we are covering what is topology, a quick bit, what are the challenges that we face, how to overcome. Is topology at all a difficult subject to learn or not? It contains a lot of abstractions and difficulties. What are those? How we can visualize topology? What are the writing of proofs are concerned? What mathematics do I need to know? That is a kind of a prerequisite. How to improve what is called an abstract thinking, which is important. What are the best books? What are the sequence in which we should read those books? What are the YouTube lectures? And a small and pleasant surprise. So these are the topics that we are going to cover, and let us quickly go ahead because this would be a fascinating journey through which you are going to enjoy and learn a lot of new perspective of this subject. But first of all, what is topology? I really don't need to go further into this because I've made a couple of videos where I've expanded. So you can just, it is just a quick kind of a glance. You can see on your screen that I have mentioned it comes from two Greek words called place, that is topo, and logy, which means subject, and it deals specifically with properties of space that does not change when it is distorted, wrapped, or twisted. This is very important. As I told you that I'm not going to expand all those terms, etc. But just for a quick overview, remember that topology deals with geometrical shapes and which are turned and twisted. Now, obviously, when a particular object is turned and twisted, there is a chance that the properties might get changed, but however, it is not. Why it is not? Because if the properties becomes changes, then how will the mathematicians or we will learn those properties? The basic objective of topology is to learn the properties of certain things, and if we find that the properties are say x, y, and z, then similar things which are carrying similar properties, we can understand that this property will be the same, so it will be easy for us to learn. So as you see, the topology studies properties of spaces that are invariant under continuous deformation. That means it will not change. You can think something of the basis of a vector and a vector, that on a curved space how the basis of a vector changes from flat space to curved space, yet the main vectors remains the same. So just a quick kind of a illustrative example of what topology is. You can see this means that objects can be stretched and deformed. For example, topologically we see that a square is topologically similar to a circle, but a circle is not topologically similar to to a figure eight, which is this one. So what we can say is that, say for example, that famous example of a cup getting changed into a donut, and donut is getting changed into a cup. It's a typical example of homeomorphism, where the function and the inverse of the function both are continuous, bijective and smooth. So the basic thing is that when the cup is changing into a donut and donut into a cup, so topologically they are the same. So we want to go more into topology details, why do we do, in my playlist of topology, you can look into that. Now, just what are the shapes and sizes? You can see on the screen I have shown what is a Klein bottle, a ball, a cup, a triangle, ball. These are just quick examples that these are topological shapes, and the topology deals with the bending and stretching, how those things are happen. So this is a kind of an illustrative example of what is a topology. In general, we understand what is topology. Now here right on your screen you can see topology is the area of mathematics that describes the properties of object that remains invariant. So what I have shown is that, as you can see on the figure, that the circle is equal to a square, which in return can be something equal to a rectangle. So the circle's property will be the same as that of the square, and that would be same as the rectangle. So the property of circle, whatever be the properties, would be something similar to that of a square, would be something similar to that of a rectangle. So that is why I have written that a circle is topologically equivalent to a square, which is equivalent to a rectangle, but geometrically they are not the same. So here is a very important difference we should point out, that topologically things might be the same, but geometrically, obviously geometrically not different. How can you say that a square and a circle are same? People will find you crazy. But in terms of topology, once we understand topology, the first thing which the masters or the grad students, they find is that, oh my goodness, there are a lot of challenges. I mean to say, I won't say difficulties, but there are a lot of challenges. So what are those challenges? But not only challenges, we have to overcome those challenges, right? So right on the next part of the video coming up are the challenges in topology. Okay, so the challenges in topology and for further subjects, say for example differential geometry or the abstract or the further advanced subjects, are not basically calculations, are not basically huge numbers, are not huge triple integrals, are not second or third or even fourth order differentiation. Absolutely not. Because remember, as we climb up the ladder, as mathematics goes much difficult, the calculations would become easier, right? Until we are dealing with huge data that we do in deep learning, etc. But things will become things becomes more easier. That means we really don't have to do big numbers, calculations, etc. But what happens is that the ideas become more abstract. The generalization becomes more wider. So these are the three things which I would like to work on. You see on your screen the three ideas: abstract ideas, abstract mathematics, and concept of generalization. For each sphere in mathematics, as far as my experience goes, these are the three stumbling blocks. I mean to say, you can say these are the bottlenecks. If you overcome these three, nothing nothing is difficult. I mean to say, nothing really challenges us. The ideas becomes very abstract, the mathematics becomes too abstract, and the concept of abstraction becomes difficult to grasp. First, let us understand literally what we know what is abstraction. If you ask me, I know the viewers who are watching my video really knows abstraction. But first, let us find out on a very rigorous term, mathematically or in a literal way, what is abstraction. Right on the screen, you see I have written, abstraction in mathematics is the process of extracting the underlying structures, patterns, or properties of a mathematical concept, removing any dependence on real-world objects with which it might originally have been connected, and generalizing so that it has wider applications. Now, as I marked those in red, these are important. That means extracting the underlying structures. That means in abstract mathematics, say for example, or abstraction, we have to extract the underlying structures. Next important is that we remove the dependence, obviously. when we started with general computer programming, it has to be either on MS-DOS or Windows. Now you see PHP, Java and Python. These are not platform dependent. So we are removing the dependence. Next, what is caused is generalizing it so that it has become wider application. We will soon see what it is. I will show you one by one. So first is that, okay, let me show you with a figure. Right on the screen you see these are mathematical structures. Let us say whatever be the mathematical structure. I'm not considering any group theory or category theory. It is a basic mathematical structure. So what are the three important points? First is that we have to have a process of extracting. That means the process that there should be the underlying structure should be extracted. So we extract that. Second is that generalizing and removing dependence. So we are not dependent on anything. That, for example, mobile, it is not that we only make calls, right? We make WhatsApp, we make video calls, we read books, we make Zoom meetings with the professionals. So it is removing dependence, and it is much more generalized. So mobile is not mobile. It has become something very generalized today, and obviously it has wider application because you can read a book, you can listen to radio, huge amount of wider application. So this is what we call is as an abstraction. So when we talk of abstraction, these three things are important. We have to extract something, generalize, remove the dependence, that we are not dependent on anything, and wider application. So this is what is called a general form of abstraction. Now you might question that this is something we are learning on topology, so where it goes? So here it comes. Topological structures also, you will see there is a process of extracting, generalizing, removing dependence, and wider applications. That means we will see soon what do we mean by removing different dependence from Euclidean Cartesian coordinates and moving into a much more generalized coordinates. Okay. Let me give you a quick figure so that these concepts with an example always becomes easier. Here you see on the screen that the earlier 3310C mobile, my father still has that old one, right? So this mobile, now when we generalize, extract and remove, you see what is happening. We can use a camera, we can do shopping, we can make video calls, we make messaging, net banking, edit videos, make calls, read texts, so that it becomes much more generalized. So this is the typical, I use mobile because this is something we use daily. So this is the concept of abstraction and generalization, because generalization and abstraction are both of them are related to each other. We will soon see in the definition. So we understood that how things become much more generalized, wider to use. Okay, how it happens with topology. Right on the screen you can see that all these polygons which we considered either to be Cartesian or Euclidean polygons, now it gets much more generalized into any kind of a shape. So as you see on the screen that polygons gets generalized into any kind of a shape, and now these shapes have generalized that the point, distance, inequality, angles, lines, plane, postulates, congruency, everything gets much more generalized. Right, everything gets modeled. That means angles are there, I mean to say in topological sense. Distance is also there, inequality of triangle is also there, postulates, lines, planes, everything are there. Everything is still there, but it has become much more generalized, but it has removed the dependence. That means we really do not depend upon specific platform, that it has to be on a plane or a circle or a square, and it has become much more wider used. So wider use means these shapes can be bent, twisted or deformed, just as we learn, through smooth continuous deformation, and it has got wider application because once a circle gets generalized into a platform which carries the properties of a circle but can be used for much more wider use. You see the significance that it becomes wider, it becomes generalized, and it is not dependent on a platform that it has to be on a Cartesian coordinate, etc. It can be used to anything. Okay, so this is what is called an abstraction, right? So what is generalization? Again, we know that things when it becomes generalized, but let us see a rigorous kind of a definition. Yeah. A generalization is a form of abstraction whereby common properties of specific instances are formulated as general concepts or claims. So generalization posits the existence of a domain or set of elements as one or more common characteristics shared by those elements, thus creating a conceptual model. So what are the key factors? It is also a form of abstraction. One, Second, the existence of domain or set of elements. Second, and third, it creates a conceptual model. So you see, abstraction and generalization, now these are very closely related to each other, and I just showed you that how topological abstraction takes place. Just to give you a kind of a figure illustrative demonstration, you see on your screen when the mind makes the generalization. So you see on the screen that something, a kind of a green thing which gets generalized either into a pine tree or a plant. So the mind makes up that green object and it generalizes into something. How topology is dependent on this? Right on your screen you can see this circle, cube, rectangle, square. So from Euclidean we are moving to non-Euclidean, from specific shape to irregular shape, from Euclidean axiom to topological axiom, and from metric or distance to a broader system where we need a totally different space which is called a topological space. Now, viewers who are watching this video, you might find some of the figures or some of the writings on your screen are not clear. I would request to go back to my video on Beginner's Guide to Topology or Building the Basis of Topology. Sorry. So you will find those in a clear way. So I have taken those, though might not be fitting on the screen right now. So we understood what is abstraction, right? We understood what is a generalization, and we also understood how it takes place in terms of topology. So the question that crops in your mind is that we understood all those things, but is topology very difficult because abstraction and generalization are not easy for the mind to train up or to understand? That is coming up in the next part of our video. So is topology difficult? Obviously, when I being a very optimistic person and I feel all the students and young mind can get trained into topology, my answer is no. Topology is not difficult, it is easy to understand. So what are the things, next question, that we need to equip ourselves in order to know topology? That's the question. So what we need to do is this. A course of rigorous proof-based abstract mathematical understanding, calculus, obviously 1, 2, 3, 4, set theory, power to visualize, able to write proofs, and a little bit of differential geometry. Right. So why I am telling proof-based? Because topology is a proof-based system. We will see what is a proof-based system. Yes, you need to understand what is a little bit of abstract algebra, and the most important thing is the set theory. You need to know set theory without doubt. Right? Now, when we talk of a proof system, and herein comes the first bottleneck, that what is a proof system? I would just like to show you a very quick example, although you know here on your screen what is called is a proof system. So you see it is raining, statement A is true. If it rains, obviously the ground becomes wet. Statement A implies statement B, and from that we prove that the ground is wet. I'm going to say this is too rudimentary, too easy, too simple. But anyway, so this is what is called a proof-based system. So first the thing is that let us now first, once we have understood what is abstraction, generalization, and whether topology is difficult to learn or not, first of all, let us quickly learn something that we really cannot visualize. Some kind of a definition. Let me show you, it will become easier. So right on the screen I have given a kind of a what I would say a definition of topological space. So you can read through it. I'm not going through it again. So let X be a non-empty set. A set T of subsets of X is said to be on topology on X if these conditions are true. X is an empty set, phi belongs to T. The union of any number of sets of T belongs to T, and the intersection of any two sets T belongs to T, and the X and T is called topological space. Okay. Now, the moment you read this kind of a definition, the first thing comes that what are those things? I'm just teaching you the step by step when topology will become interesting. So you see right on the screen, empty set, open set, closed set, union, topological space. What are those things? Actually, what are those? That becomes the first initial, I would say, bottleneck, that we are unable to understand those things. We are unable to visualize those things. So now if we take the definition, what is an open set? May I show you what is an open set? See on the screen. Open set is a method to distinguish between points, and here we measure much the topological spaces without confining to the definition of distance. Now, so you see that we are moving ahead, we are making it platform free. But the question is that what on earth that this makes meaning? I cannot really see what is an open set. Same goes with this one, homeomorphism. So let x and y be topological space. So if the function of x maps onto y, it is a bijection. If both function and inverse are continuous, f is called homeomorphism. So the important thing what I'm trying to tell in this part of the video is that this closed set, open set, bijection function, now what are those things? What can we make out of that? These are just lines, really makes no sense. So the question that rises right now is that how can we visualize topology or definitions? How can we see? Because until we see that, those things, we can't do the mathematics. The entire show becomes useless. So how can we visualize topology? That is coming up in the next part of our video. I would like to show you the same definition of topology and topological space, what we just read now, on a visual format. Right on the screen you see, you can just go through that. Here you see I have drawn X to be a set, and you see that T to be a subset. So union of set, so if there are certain other subset, set 1, set 2, set 3, and there is the intersection, set 1 intersects with set 2, intersects with set 3, and phi you see I have given as an empty set, and X, it contains certain elements like 1, 2, C, V and T. So now you see, now you can understand what is an empty set. The union of any number of sets T belongs to T. So I have shown you the union. The intersection of any two sets T belongs to C. So there are sets 1, 2, 3, 4, A, B, C, whatever. There's an empty set. There's T, a subset. There's a set called X. So once you start visualizing those things will become easier. So that is point number one, is that how to visualize, and you need to draw those things on a pen and paper so that it becomes easier. Same goes with open set. Right on the screen you see open set provides methods to distinguish between 2 points, and the concept of nearness without confining to the definition of distance. So you can see on the screen that there's a S, there's a T subset, and those points which I have drawn are nearness. This is near to this is near to this, right? So the concept of nearness, won't be clear until you draw on pen and paper what is nearness by mentioning 2 points, arrows, this is nearness, right? So now open set and nearness is clear. Empty set phi intersection becomes clear. Same goes with what we learn, homeomorphism. Right on the screen I have just shown a basic kind of a definition, illustration of what is a homeomorphism. You can see X and U, and there's a function which is going and an inverse function. So all those things, what I would recommend, the first thing that you need to do is that whenever you come up with a definition in topology, or even in real analysis also, or in differential geometry, this kind of a proof-based system, please draw those things. Until you draw them, it won't become visual to the mind to understand. The moment it will become visual to the mind, mathematics will become easier, proofreading will become easier, everything will become easier, right? So another example I would like to show you right on the screen is that this X equals to ABC. I have shown it in my previous videos, that see ABCs, all those circle and round, these are different topologies. These are different kind of topologies. First one, second one, right? So whenever we are talking of topologies and elements, because we are not dealing with points anymore, those elements of a set are the points, right? I have elucidated in my previous videos. So the first thing, I hope it becomes clear, that you need to draw. You really need to take a pen and a paper when you get this kind of abstract definitions, draw it. But the next most important thing is yet to come, is that you need to do a proof-based system. So what is called writing proofs, coming up in our video immediately now in the next part. Okay, so when we talk of writing proofs, what do we mean? what do we mean? Let us see what do we mean. So right on the screen you see these are 1, 2, 3, 4. These are called proofs. So prove that something is not homeomorphic to the subspace. Prove that every compact Hausdorff space is a normal space. Prove that so and so and so. Right? So these are proofs which are going to come, and you need to be very much aware about how to write a proof. Now, I would just like to show you a basic structure. I'm not going to teach you what is a proof system, you already know, or maybe I can make a later video on how to write a proper proof. So there, right on the screen, you see a basic structure of a proof-based system. So there is a beginning, there is a middle, and there is an end. Right, so this is how we do. And here is something which I would like to show you. This is a kind of a typical example. So we are required to prove, so there are certain things which are given, and we assume, that means certain things are assumed. Suppose that P is a limit point those and those, therefore every limit point of A must belong to A. So this is how we deal with proof. So let us see what are some of the useful points, because this is not a video to write proof. So number one is that write out the beginning very carefully, write out the definitions explicitly, write the end also carefully, try and manipulate both ends and make them look into another, take big leaps when it happens and see if the situation reminds of the earlier situation you have dealt it, and then you can do a copy and a paste. So when we are learning that how we should learn topology, first thing is that you have to be very much aware and very much systematic based on writing proofs. Without a proof, without a knowledge of a proof-based system, we cannot go ahead with topology. Again, it casually came in. So very important is that you need to have a knack towards writing proofs. You should do proof system, a beginning, a middle, and the end, logically proving backwards, all those things. So proof-based learning or going through a course or anything which has got a proof is very important. Now the question is that when we are dealing with proofs, logical, Boolean, logical operator, etc., the most important thing which comes in the mind is that what are our prerequisites to learn topology? That means what mathematics do we need to know previously in order to know topology? Coming up in the next part of our video. So to be very honest with you, because topology has got different branches: algebraic topology, differential topology, geometric topology, general topology. So to be very honest with you, topology really doesn't demand a huge amount of mathematics, that you need to know a huge amount of mathematics, lot of things, no. But what topology requires is what is called a mathematical maturity. A mathematical maturity for Terence Tao, it came at the age of 16. For some people it comes at the age of 61. So we really cannot comment on that, but there are certain ground rules that you need to know. Right on the screen you see here. You need to have a thorough understanding of real analysis, set theory, differential geometry if possible, group theory if you're dealing with algebraic topology, and a proof-based mathematics. Now, you might say that, is it absolute that I need to know real analysis? No, I won't say it is not absolute to know, but it is essential. I'm going to say it is better that you have real analysis under your sleeves. And when I say under your sleeves, means you really understand real analysis, you really can, make those proofs right, because from real analysis, if you move to topology, it becomes similar, not in terms of the conceptual understanding, but those proofs. Set theory, obviously, every moment we encounter the operations of set theory. Differential geometry, if possible, yes, not required, because some part of differential geometry and topology will be overlapping. If you're dealing with algebraic topology, you need to know group theory and obviously the proof-based mathematics. That is escape, I mean to say. Now, all those things, when we are talking of real analysis, etc., all those, again, these are very abstract things. As we saw, abstraction and generalization. Question is that how can we improve? Is there any tool we can improve abstract thinking? Let us see in the next part of our video. So in order to improve abstract thinking, although there is no rigorous any kind of a flow chart that do this, what I would like to show is something very interesting observation. First is that from a child who learns from 2 to 7 years, what they do is that they learn think symbolically. So they use a lot of symbols from 2 to 7 years of understanding. This is not my research. This is something which is done by the psychologists or people who are dealing with those. 7 to 11 years is logical reasoning, right? You start to think something logically. 12 years onward, it is abstract thinking. What does that mean? That means you already know abstract thinking. That's the good news. You already know what is abstract thinking, but there are certain things you need to exercise, right? So nothing to worry about. This is not certain foreign things that you need to now exercise and do. You already know because you're post 12 years. I would like to give very simple points. Number one is learning a foreign language. Now, this is true for me. I can say, this is true for me. I can say because apart from English, I know Arabic, I know Urdu and some part of Persian and a little bit of German. Not really to say that I know German, right? So what happens is that when we are learning a foreign language, especially those whose scripts are not Roman, I mean to say, for example, Chinese, Japanese, etc., then we have to, make a lot of understanding and draw parallels with English alphabet, b, k, t, etc. So alphabets actually creates a lot of abstract thinking because here you have nothing similar, so everything is abstract. Grammar, because the grammar of any other language, now if it is very much similar to English, cannot help it, but something which is, for example, German grammar, it is totally something different. Arabic grammar, something totally different. You do learn grammar, that is also abstract thinking. Sentence making, so the way I am talking, it might not be the same way in which we talk in German, in the which we frame the sentence in Spanish, Italian, Persian, right? So when you make sentence, it is abstract thinking. Thoughts and ideas, because the way we used to think that, say, for example, my name is Shonak. So, right, so this comes first, the verb comes at the middle. For other languages, it might be different. The verb comes right at the beginning and then it happens. So what I'm trying to tell is that these things, learning a language, any kind of a foreign language, it improves abstract thinking for sure, right? Other than that, solving puzzles, you can see on the screen, building 3D models, explore optical illusions. What do I mean by optical illusions? Let me show you this one. Ability to write similes, metaphors, analogies, and solving complex problems. So it is not that abstract thinking is only through mathematics. Wrong, very wrong. So when a child is being taught, a young person is being taught that Mohenjo-daro, Harappa civilization, mythology, Egyptian mythology, so that person or that candidate is transcending him or her to a location, right, where he or she is now into Mohenjo-daro, walking by the seaside, writing essays, metaphors. All those things also improves abstract thinking. So it is not that it is only mathematics. First is grammar, second solving puzzles, writing metaphors, solving complex problems, and optical illusions. Yes, it helps, but you see, right, as I flashed on the screen, that sometimes it looks like a person playing a guitar, but it is an old man's face. So given an optical illusion problem, and when you ask a candidate, a person to solve it, then that optical illusion also serves as an exercise to improve abstract thinking. So now we know what is abstract thinking. Now we know what is topology. Now we know what is proof writing. Now we know why we need proof writing, and also we know how to visualize topology in different sense. We come to the central and most important part of the video, that is how we learn. We know what are the books and how we should read those books, coming up in the next part of our video. There are a good amount of books in topology. If you talk to me frankly, before making the video and earlier also I made an extensive research, considering more than YouTube lectures, books are very good. So what I would say, 1, 2, 3, 4, 5, 6. So I've just taken 6 books. Okay, and The good news, the surprise that you have been waiting is that I have got all those 5 books. That is a surprise. I just thought to break the surprise now. I've got all those 5 books. I will tell you. These 6 books are going to be a Bible. Not much are required. More books you read, more books you purchase, it is a wastage. You get more confused. Just I will expand on those 6 books and I will tell you how to read that. Right on the screen. First is Topology by the famous Munkres, that the classical topology book, which we all know. The second is Bert and Mendelssohn's book. Third would be called Topology Illustrated. Fourth is Topology Without Tears. These are the first 4 phases, the first 4 books. Next, right on the screen, Introduction to Metric and Topological Space by Sutherland, and From Geometry to Topology by H. Graham Flegg. So I would like to tell you, let me give you the table of contents and the idea of the book, then I will tell you what are the sequence that we do. First is that this Topology by Munkres. It is a famous classic book. Any grad or undergrad must have read it. I would recommend strongly to go ahead with the book. This is the best book for beginners. It assumes nothing, absolutely nothing. Only knowing set theory, it will help you. Extremely easy, lot of illustrations and easy explanations. So this is a big fat book, right, Munkres. So it will start first teaching you the essentials of set theory and then take you slowly one by one. So it assumes nothing and it is the best book. Right on the screen you see these are some of the table of contents. So the set theory and logic is covered in details, and then the topological space, etc., etc., all these are covered, right? So first is Munkres, excellent book. Starts with theory, set theory, and there are a lot of illustrations. That is what we are calling that. Until you draw, until you make the figures, you won't be able to visualize. That is essentially confirmed. Second is this Bert and Mendelssohn's book. This is precise, not lucid, to be very honest. Not much illustrative, and it has limitation. It just covers up to the Bolzano-Weierstrass theorem. So this is a kind of a, I won't say difficult, but it's a kind of a okay kind of a book, right? Third would be Topology Illustrated. I'm thankful to one of my subscribers, Rahil, who gave me this book. So this is a very good book. I mean to say, huge amount of illustrations are there. You see on the screen 1000 illustration, 1000 exercises. It focuses but on only algebraic topology, particularly on homology, and it is very clear, lucid and easy. The problem is that it specifically concentrates on homology and algebraic topology. So if you're taking up algebraic topology separately, this is the best book. I mean to say, it is a wonderful, it is #1 book because it contains huge amount of illustrations, colored photographs, etc., which makes things easy, which makes things very easy to understand. Next book would be Topology Without Tears. I got in touch with Professor Sidney A. Morris, excellent person. It is very good for beginners, clear, simple and lucid, lots of proofs and definitions are pure and simple. And most important is that I think that, yeah, it is there. So you can go to this topologywithouttears.net or something. I really don't know the address specifically, and you can find a lot of videos. Great videos on real analysis, mathematical proof. That is the building block of this. Sidney Morris, Topology Without Tears in Facebook. Even there's a group called Topology Without Tears. Oh my goodness, it's an absolutely great book. Very simple. Lot of illustrations and proofs are given. It is a must. Introduction to Metric and Topological Spaces. Oh my goodness, this is a real handsome book. It starts building with the basics. Most importantly, what it does, it starts from real analysis. Now, here I would like to tell you what Professor Sutherland has done is that, because as we are talking that it is a proof-based system, so in this book he has started dealing much with real analysis first, and he has written in the preface that the students might get bored, but hold on, we are first touching base with the real analysis. The reason is that from real analysis, moving to topology becomes easier. I mean to say conceptually, because that also deals with proof-based system, this also deals with proof-based system, isn't it? So this starts from real analysis. Emphasis is given more on compactness, connectedness and closeness. Step by step teaches a lot of real analysis. clear, lucid and simple explanations. So I mean to say, this is really a wonderful book because you first brush up with your concept of real analysis, and as I told you, from real analysis going to topology really makes sense because those are I would say philosophically they are the same. Last, most important book right on your screen, I have given a thumbs up, best choice, From Geometry to Topology by H. Graham Flegg. Graham Flegg was a professor of mathematics, mostly into history of mathematics. So it starts with geometry to topology, explains geometry, explains metric space, extremely simple to understand, and lot of illustration. Now you see why I told you best choice, because okay, let me show you what the author says. Right on the screen you see here it says, most university courses in topology plunge immediately into formalized and entirely abstract presentation of topological concepts. Students often find it difficult in the early stage of such courses to get any real sort of feel for the subject. Even the more simple ideas become difficult to grasp if their simplicity is obscured by the familiar formality of the language in which it is being presented. On the other hand, there is often insufficient time available for more intuitive, with the aim bridging the gap, last line, bridging the gap between intuitive and largely geometrical ideas in the formal study of topology. So this is the book, mark my words. Sorry. This is the book because the author himself says that university textbook directly plunges into this kind of a definition, right, which we saw. Let X be an open set, phi be an empty set. But in order to know that, in order to get a grasp or intuitive understanding, what is required is the link between geometry and topology. Until we understand that where geometry has got its limitation, there is no use of learning topology, isn't it? So this is one of the best books. So now that we have seen the context, the texts of the internal matter of all those books, the question comes that what are the books that we first start with? So right on your screen, you see I have given chronology of reading. First would be Graham Flegg's book. Then go into introduction on metric and topological space. Then you go into Munkres. Then you go into topological with tiers, and then introduction to topology by Bert and Mendelssohn. This is the sequence of study. Now you might ask me why? Simple, because from geometry to topology gives you a kind of an easy understanding that these are the limitations of geometry. So we went into topology. Next comes introduction to metric and topological spaces. Again, it is important because metric first is the Euclidean space, then the metric space, then got to topology. If you have seen my earlier video, I have clearly shown how the evolvement happened. So metric, I would say metric space and topological space are very much related to each other. So the basic function D which we use in metric won't be in topological space. That is the only difference. So second book would be that metric. So first start with geometry, Euclidean geometry, then we go to topology, the first book. Second, the limitations of metric space, then go into topology. Third is the book of Munkres, where you get all the basics of set theory and then deep into topology. Then comes fourth book, that is topology. One thing which I would like to tell you that these are the 5 books and the 6th book obviously. So don't go ahead purchasing too much of books, downloading books, doesn't make any sense. Just go step by step. Start with the Graham Flegg's book. It is easy to understand. Okay, so we come to the last part of YouTube lectures on topology. Now, before starting this section, what I would like to tell you is that on internet, what I have seen, the lectures of topology, there are much more into Hindi language. Like, so if you really understand Hindi, then there are good many lectures. I remember the person named Gajendra Purohit and various other lectures, so you can go ahead with those Hindi lectures. What I would like to show you, just few YouTube lectures. Why few? Again, because as I tell that going ahead with too many lectures confuses. First would be this one. N.J. Wilderberg, very famous person. You must have seen him giving lectures mostly on history of mathematics. His channel Insight into Mathematics is just wonderful, and the first thing to start with topology. Why again? Because you will see most of the lectures of N.J. Weidelberg, he starts with the history of topology, history of mathematics. It will be very easy for you to understand. So first would be N.J. Weidelberg's videos. Second is this one. This is, I think, IIT Madras, and there is Professor P. Veeramani, Department of Mathematics. It's quite an old lecture, so you won't find those whiteboards or projectors. So he used to use those green boards and write in chalk, but absolutely down to earth. And what a fantastic person, and what a fantastic lecturer he is. P. Veeramani, IITs and ISC. This is NPTELs. So University, IIT Madras. This is an absolutely great, I would say, lecture to watch in. Third would be this one, Marius Furter. You see on your screen, it started with compactness 1, 2, 3, and then it further goes into sequence. It is another channel which you can go ahead and watch. This is absolutely great in terms of learning topology. Next, I would, very interesting, I found Elliot Nicholson's channel on topology, and not only topology, you will be surprised to see, and go to Nicholson's this YouTube channel. He has got videos on plastic surgery, on bacterias and whatnot. I mean to say, it's huge. So here you will find many good videos building up right from the basics. Elliot Nicholson. Then I would like to give another person. This is Daniel Chan Maths. You go to his videos. He's got a lot of videos on category theory, group theory, and specifically into topology, right? Next comes a little bit advanced, but a very good channel, James Cook, right? James Cook also had got very good videos on topology, which you can definitely watch. Last, as we call last and not the least, I would say last and the best on the YouTube, Dr. Tadashi Tokieda, and his lectures on topology are just phenomenal. I think this channel is some African university channel or something. Anyway, you can just have a look onto that. Now, what Dr. Tadashi does is that he used to stand on the bench, right, jumping up, and construct certain shapes, take papers, etc., and used to create a Mobius strip, used to create a non-orientable surface, right? So not only the lectures become very important, but as I have told you, I have made a very old video, if you see, using my daughter's colored clays, how you can really create a kind of a circle, and then you deform it into a kind of a rectangle, or etc. So the what Dr. Tadashi does in this kind of a lecture, you will see, you can go and watch it in YouTube, is that he first makes those things with a thin sheet of paper and then further goes into lecture. I would say he's a phenomenal lecturer, the best in terms of his video. So these are the YouTube lectures. Again, as I would like to tell, that do not go and do not delve deep into too much of lectures. Take one particular lecture, for example Dr. Tadashi's lecture, and then you learn deep into that, or take N.J. Weidelberg's lecture and go deep into that. That is, I think that would be more than sufficient. The video is almost, I have completed whatever I need to discuss. So I won't be summarizing this video right now, because we have covered many topics. The sun is out, it's a bright morning, and I feel a little bit chill. So really very happy that the winter is coming, and the winter, I can say, almost has arrived. Just before signing off from today's video, what I would like to tell you are few key points. First, let us understand that topology is not at all difficult. Right, that was the purpose, to motivate you and make you understand. Number one is, topology is not at all difficult. If you find it difficult, then reason is that perhaps you are not getting the right book, you're not following the right path, and perhaps you don't know why topology is being discovered, or why we deal with topology. Go to my playlist on my channel, Physics for Students, and you can find out the details that why topology is important. So number one, topology is not difficult. Number two, it is quite easy to understand. Third is that before going deep into topology, do understand what is a proof-based system, if possible a little bit more into real analysis or any kind of a rigorous proof-based mathematics class. Next important is that visualization. Whenever you are getting any kind of an abstract definition, say theory or otherwise, you are unable to understand, please draw them. I would request, please draw them. Drawing really helps, figures really helps, it assimilates into our brain faster. So draw them, then go into understanding abstractness. You can start exercising your mind on abstractness. What is abstractness? Why do we need abstractness? I have shown you that abstractness is required in order to generalize and put everything in one go. Mobile phone, again an example. Once you have understood abstractness, visualization, then start with the books. Start with the book that I have shown in sequence, Geometry and Topology, then go into metric spaces, then go into Munkrestbook, because again a wrong book will destroy everything. I am telling you, a wrong book destroys everything. So go sequentially, step by step, complete the books, then go into my videos in topology. I have just started building the basics. So all those videos, what I am doing is visualizing using photographs. I am already coming up with another video which is just the topic that much which I have dealt with, how to visualize through pictures. I hope you liked today's video. It's a complete guide on topology. If you need, I'm so sorry. Last thing is that if you need all those books, if you really need all those books, please write to me in this email ID. Please write to my Gmail ID, and what I will do is that I will share all those books except the Burt and Mendelssohn's book. I have got all those books. I will share the links. I can email you or I can share it in Google Drive. So that was the last surprise which I told you. I told the surprise earlier also. Please email me and feel free to comment on my video. Please subscribe. Please click on the like button. Please click on the bell icon and all to get all the notifications of this video. And this is Shaunak signing off from Physics for Students, promising you again to come back with yet another very interesting video which I am sure that you are going to enjoy. Please put up your comments and let me know how you like the video, and best wishes, and stay safe and happy. We'll be back very soon with another video. Till then, goodbye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.